Okay, we're live. Just kidding. This is a recording. But all right, how's it going, guys? My name's Zach. I'm with Slate Robotics. This is the Slate Robotics podcast. Let me move my microphone a little bit closer there. Hopefully that's good. A couple changes since last time. This is nice, isn't it? My brother-in-law, Jake, made this. He cut everything out, and he does a lot of woodworking. Painted it all. It was a Christmas gift. It's really cool. I've always known I needed something on the background because it kind of looks like a prison in here. Uh, it's a normal storefront that we're working out of in our shop, but um, this is our one concrete wall, I guess. It's really not that bad. We have other videos actually of I give a tour of the place a little bit more, so you can see those on our channel if you're interested. Okay, so today, episode number 2 of the Slate Robotics podcast. This is good, all right? We are going to be talking about, well, actually, I'm going through Reddit. I've picked out, it looks like 6 questions so far, where I'm going to go through the robotics subreddit, and I'm going to help answer some questions that I think I can provide some value to. Now, there's a bunch of questions where people ask things, and I found a few where there's like acronyms that I've never heard of before. I mean, robotics is a big field, so I don't claim to know everything about robotics, but there are some basic things that I could definitely help with people that are new to robotics or people that are trying to build things that I've built before. So I think this will be a cool concept. So that's what today's video is going to be. I've got 6 questions lined out. Now I'm not going to be afraid to go for the low effort questions. There's a couple questions on the robotics subreddit where people ask like the same question every week. How do I get into robotics? How can I get a career in robotics? How can I learn more about robotics? Like these really vague questions. And those always get downvoted because they get asked every week, and they're generally pretty low effort. Like generally people want to see some effort on these posts, but hey, not a problem for this podcast. We're going to go ahead and try to tackle some of these lower effort ones. Some of them are good questions, but you'll know the low effort ones when you see them. They usually have one upvote. So I think this will be great. Cool. I've got my time. I'm going to try to keep this under 30 minutes. That's the goal. It could be really short. Who knows? Okay. Wrong one. There we go. Testing everything out with my setup. I'm still going to be learning and getting better. First question. You can see my notes on the side if you want to jump ahead. I am not going to add the timestamps, but if somebody wants to do that in the comments, that'd be great. Okay, so first question. What's a type of motor / servo / actuator that can be physically moved? It's a long question. Hey, so I'm not an engineer by any means, but I do lightly dabble in electronics now and again, though never in motor control, and I'm always full of bad ideas. Without going into too much detail, there are a number of applications I've thought of where it would be extremely beneficial, if not necessary, to be able to physically move the item being controlled by an actuator. Usually not while it's in motion, but at some point after its installation without damaging the actuator, or in some cases of positionable servos, having it lose its spot and require calibration. To give just a single example, I have a vehicle with a split tailgate, and I would love to allow it to open automatically. I already see it's easily possible to mount linear actuators in 2 or 3 spots to make this happen. However, each linear actuator I look at is perfect for the application with one exception. You can't move it if it's unpowered. This would make the tailgate electric only, which is not ideal. I'd prefer to be able to manually open the tailgate, even if there's some extra resistance. That's totally okay in most of these applications, but I find that with any actuator or servo that I find, if its position is physically changed while it's unpowered, there's a risk of damage to it. The thing is, I know these have to exist. Car door lock actuators, for example, are linear, but you can use mechanical force, key turning, or even pushing down on the lock rod to override the position of the actuator. The position the actuator is in, and it does no damage. I feel like I must be misnaming something here, and that's why my search has come up empty. Is there any special type of servo or actuator that would fit into this category? Basically, my question is, for you robotniks, do these even exist? Robotniks, never heard that before. Can they be purchased? What are they called? Am I crazy? What is the meaning of life? Thanks in advance. That's great. Okay, so that was the longest question of these, so don't worry. We're not going to have 3 minutes of reading for every question. So the question you're asking is for an actuator, the key word you're looking for is backdrivability. Backdrivability means that you're able to take the output of the actuator and physically turn and move the angle. That's the key word you're looking for, backdrivability. It's not used a bunch, that term, but typically with robotics, that's what they'll talk about. So if you have a robotic arm, you'll have non-backdrivable arms and you'll have backdrivable ones. Backdrivability is expensive. There are a couple of different ways. I mean, we'll just talk about it broadly, but there are a couple of different ways in order to achieve backdrivability. And this will help kind of understand, and I'll get into a little bit of how I think you might be able to manage that question. Let's jump over here. So we'll use my whiteboard, and I'll draw real big. So this is a motor with an output shaft. Now, these motors are going to be running at like if this is just normal like 12 volt 12 volt DC motor, and this is something you buy off of Amazon. I mean, at the low end, this is going to be running probably like 5,000 RPM. At the high end, it's going to be running 10,000 RPM. I'm sure they make DC motors that run faster than that. So this thing's moving super quickly, and it is relatively low torque. So if you have just a normal DC motor, there's no gearbox on it or anything, it's going to be running really fast, and it's going to be having low torque. Now, for most applications, you don't actually, unless you're powering like a car or something like that, you don't actually want the output shaft to be running at 10,000 RPM. Like if you have a robotic arm, and like just one of the joints, and this thing runs at 10,000 RPM, let's assume it had enough torque, it would be a nightmare. It wouldn't work. It would crash into itself. You would never be able to fine tune the position. It's too fast, right? So you have to slow it down. And you also have the problem of, well, there's probably not enough torque. I mean, you're probably getting, gosh, I don't know what the torque output of something like this is, but it's gonna be like tiny. I mean, absolutely tiny. You're not gonna be able to turn much with it. So what's the perfect solution if you're moving too fast and you don't have enough torque? The perfect solution to solving that problem is a gearbox, because a gearbox is going to bring down the RPM, and it's also, well, a gear reduction gearbox. It's going to bring down the RPM. It's going to bring up the torque dramatically. So people will attach a gearbox, and this will all tie into the question of backdrivability. This is my gearbox. So the gearbox is going to have a bunch of gears in here, and depending on the type of gearbox it is, yada yada. It's beautiful, isn't it? Depending on the type of gearbox, it's going to depend on the type of gears it's used, etc. But it's going to have basically the input shaft, or the output shaft of the motor is going to feed into the input of the gearbox. And then the gearbox itself is going to have an output shaft. And then that's where you can attach, if you want to do some sort of belt setup or something like that, that's where you can attach your stuff on there. So far so good, right? Gearbox is relatively low cost. You can have, what kind of, you might have, a 200 to 1 gear reduction or something like that. I don't think that's too extreme. Where you might be able to bring the speed of this, well, if this was running, let's do math. If this is running at 10,000 RPM, and we want to get that down to 100 RPM, then we're going to need a 100 to 1 gear reduction. So we need a 100 to 1 gear reduction. So that means for every time the motor turns, the output here is going to turn 1/100th. So in order to have a full turn of the output of the gearbox, you're going to need to turn the motor 100 times. Okay, so far so good. Now, where this goes wrong in your case is that whenever you have a large gear reduction, the way gearboxes work is basically you get, like, the friction doesn't, each gear that you add, the friction doesn't like multiply exponentially as the torque goes from here to here. But the problem is when you try to turn the output shaft from the output, like you try to physically turn the output here to try to get the motor to turn physically, all of these, each one of these gears has some level of friction in them, where so there's going to be some coefficient of friction where, I apply 1 Newton meter of torque in this rotation, but 5% of that is going to get burnt off as heat. Like there's no free lunch here. So you're losing torque the more gears you add because of some coefficient of friction. But and I want to preface all this by saying I'm not a mechanical engineer. This is just based on what I know about just my background in building robotics, or robots, right? So I might be getting some of this wrong, but in general, this is right. So there's some coefficient of friction, but when you're going from the motor to the output, the coefficient, like you're still getting a 10-to-1 gear reduction, but 5% of that torque gets lost. But from here down, that friction magnifies when you go the other way. So that makes it, the bigger gear reduction you have here, that makes it more difficult, and it increases the amount of torque exponentially that you need in order to turn the output shaft. So whenever you've just got a motor without a gearbox on top of it, you can turn the motor easily, and you don't have to risk damaging it too much. But when you add one of these gearboxes, which you need, right, because this motor is going to be too fast and it's not going to deliver enough power, then you basically have this problem of, well, you have enough torque to do what you need to do, but you don't have the back drivability. That's the one thing that you're going to lose out on. The problem's even worse with linear actuators because they're going to be using some sort of gear, well, most likely. Yeah, they would have to. They're going to be using some sort of gearbox that is not back drivable by design. So you have, in this case, a normal spur gearbox is technically back drivable, but you have this problem of the friction magnifying as you go from the output to the input. You're going to have other gearboxes. Okay, this is going to be great. Just assume this is part of the gear over here, right? No, that's a bad example. The example I'm going for is with a worm gearbox, where you have a rod with these. It's basically like a screw next to a spur gear. Yeah, this is really bad drawing, but basically my point is, with a spur gear or with a worm gear assembly, it's physically not back drivable, which means that there's no problem of friction here. The actual problem is that it only is designed so that the torque can go from the input to the output, not the other way, because there's a physical constraint here based on how the screw in the worm gear is turning in relation to the actual spur gear. So you're screwed there, and that's why linear actuators in general, you're not going to be able to have back drivability with those either. So now with cheaper servo motors, like the ones you get off of Amazon, and most servo motors, those are back drivable. And the reason they're back drivable is because there's not very much gear reduction. It's going to be a smaller motor, and there's not going to be a high gear reduction on top of that. So you can turn the output with fairly decent, fairly easily, right? Another problem is with these high gear reduction gearboxes, you're most likely, with the gears that are in there, if you try to turn the output, you're probably going to break the gears that are in the center here. Okay, so I've talked a lot about the problem. I've talked at length about the whole problem here. So your solution, I mean, you could have a specially designed motor, and I don't even know how you would design this, but this would be like, something that we would hope to get to at one point in the future, where the motor itself is low RPM, high torque. I don't know how to design that, or if that's even possible, and if it is a product out there, it's going to be super expensive. So that's not an option for you. So your other options, for you specifically, I'll go ahead and erase this. So for you specifically, you're going to have some sort of mechanism that can engage and disengage your linear actuator, or you're going to have some sort of torque feedback. So torque feedback is the way that cheaper robots are able to implement back drivability. I mean, there are certain designs for actuators that I've seen. What are they called? It's the name is missing me. It's the type of actuators that they used in Baxter from Rethink Robotics. It'll come to me in just a second. So there's actuators like that, but basically you need some sort of force feedback. So we'll use, in the linear actuator example, we have this linear actuator with the rod out here, and your tailgate example might take a little bit for me to wrap my head around to be able to bring a decent solution to. But so this is going to be your control box over here with all of your electronics. This is your linear actuator out here. So the simple way right now is you press a button and it extends out. You press another button and it goes back in. Now, if you want to have force feedback into that, what you would do is insert some sort of like a low-cost solution. I mean, you would want some sort of torque, or I'm sorry, force feedback here in order to have the well, okay. So the cheapest solution to that is going to be a FSR, force sensing resistor. So they make these little resistors. You might have seen them, like, they used them a lot in older cars. They might still use them right now, but like where they'll have the panels on the front of the car, but it'll be completely flat, and they'll have these buttons on there, but there's not physical buttons. So you push into the plastic where the label is on the dash, or on the control panel of the car, and you press that area. You're not pressing a physical button, but it still acts like a button. And the way that works is with force sensing resistors. It's able to measure the force that you're applying by, it's got this arrangement of leads throughout this thin film, and based on the way that it's arranged, when you apply force to it, it changes the resistance of the current that goes through that sensor. So you can use those in your projects to add force feedback really cheaply. So these you can buy on Amazon today for like $8, right? So they're super cheap. And what you can do is you can add that force sensing resistor into here, and you can measure the amount of force that's being applied against the output of that linear actuator. And then what you can do is you can have a program running on here that it'll behave normally with your button and all of that, but if it detects force on the output, it can drive in the direction that the force is going. So this is going to read, it's an analog reading, so it's going to read like 50% or whatever. It's just going to be sitting there fine. And then once you get a spike up to 90% force that it's reading, then you'll physically, or you'll tell the motor in the linear actuator to start driving back that way. So that's one solution. The problem you might have with that is that linear actuators are pretty slow. So that may not be the best option for you, but that would give you, so if you arrange this such that at its resting state, this is sitting at 50% of the force sensing resistance. And if you pushed in, it increases that closer to 100%. So you could just calculate the difference between its resting state and its current reading. So if it's normally at 50% and it reads 100%, then you need to send the linear actuator that way. And if it's normally at 50% and now it reads closer to 0%, which means that someone's actually applying force this way, then that would mean that you would run the linear actuator out that way. There's going to be some problems depending on the setup that you've got here, where that may or may not work great for you. But and maybe with a tailgate, that's the problem with force sensing resistors is that it doesn't read the high end of the forces. It's going to read lower levels of force. And there's ways you can get around that by maybe padding that force sensing resistor. So you have to apply a lot of force in order to get that thing to move. So that would potentially be one way that you could combat that. But that's how you would implement some sort of force feedback in order to have some sort of back drivability in that system. The other way that might just be easier from your example would be to have just some sort of mechanism that I'm spending a lot of time on these questions. Some sort of mechanism that you can basically just disengage. It would kind of be like a clutch. You just disengage this linear actuator from whatever it's controlling. A potentially dumb example you could use. I don't know, if you have, we'll say we have the linear actuator. This may or may not work. We'll see. We'll say you have the linear actuator on some sort of pivot. Take this with a grain of salt. This is going to be more of kind of the idea. This probably won't work in implementation, but you can have some sort of joint here that connects. So the idea would be that you have something here where you can pull out a pin and it's going to disengage the linear actuator from the actual tailgate. So you could pull a pin out like this, and now these two things are freely rotating and can move independently of each other. Like if this is your tailgate and you're trying to, again, they're kind of a bad example. I've just kind of, this is off the top of the head, but you would have some sort of physical mechanism where it would actually be able to connect or disconnect. I mean, that would be like one of the cheaper examples you could use, but anyway, that gives you a little bit of an introduction to the problem. The reason there's not great solutions out there off the market is because, it's kind of a hard problem. And this is something I'm working on pretty intently here, is building low-cost back-drivable actuators. In our actuators that we have for the TR2 are pretty good. They're definitely the best in terms of the cost that's available in the market. So you could look into those. We haven't published a lot of information yet on those. So I don't know. If I were you, I'd just kind of wait and see what we publish with that. But those might be able to solve your problem. So anyway, I think that's question number 1 in the books. We are 24, almost 25 minutes in. Okay, that was a fun problem though. Let's see, left screen. Cool. Question 1 in the books. Self-balancing and driving robot. I want to build a self-balancing robot that is able to drive, but I found nowhere a good explanation about how to realize the driving part. Balancing isn't that hard. If somebody could help, I would be thankful. I'll try to go through this quickly. So, self-balancing robot, you've got a wheel, and you've got a thing, and then you've got your electronics that are in here, right? And he's saying, I'm assuming your robot's set up like this, but he's saying that, or she, or Zer, sorry, and so you'll be able to sit this at 90 degrees without problems, but how do I get it to drive forward? Well, the easiest way, I mean, think about if you're standing and you start leaning forward, you take a step, right? And if you're backwards, you take a step back, and that gets you to move in one way or another. I've heard people talk about running, for instance. Running is just controlled falling, because if you're physically focused on moving the muscles in your legs, then you're going to, that's really, it's high friction. That's not really a good term, but basically you're better off using your weight and the actual mechanism of your legs to move yourself forward. So it's the same instance here. So you're at 90 degrees normally. If you set the goal position of your PID controller to, I don't know what the angle is going to be, but we could say 85 degrees. So if this is 90 and so we change this to 85 degrees, and then that would move you forward. And then if you set the goal position of 95 degrees, that would move you backwards in this direction. And the reason it would do that is, again, as I move forward, if I maintain that forward position, the only way I can do that is by physically moving the robot, right? I can't maintain an angle forward without the robot moving, because it's on wheels, right? So what you would do is you would set your PID controller, and I don't know how you have it programmed, but a PID controller, you're going to give it a goal position, and then you're going to read the current position. Although you might be using encoders. The encoder's complicated. It depends on how your system's set up. But I would get it I would configure your system such that you can set an actual angle, and then set the angle to be 85 to go forward, and set it to be 95 to go backwards. And you can increase and decrease the speed of your robot based on what that angle is. Now, there's going to be a point where there's nothing you can do. It's already too far forward, and it's just going to fall to the ground. And at that point, well, okay, how you do that is actually not through the encoders. That would be through the inertial measurement unit. So if an IMU is just a little chip that you can put on your electronics, and it'll tell you actually the physical angle. I think it's supposed to be like 6 degrees of freedom or something crazy like that. But it'll tell you the actual angle that that IMU is sitting at. So you could use an inertial measurement unit. They're like $30 or something on Amazon, and that will give you the angle here. And then you can just turn the motors with a PID controller and tune it properly such that the angle is exactly where you want it. And then your control would be changing that angle based on where you want it to drive. That would be the way that I would set that up. Okay, cool. I think the next one's a fun one. Question number 3. Help. Hi, I'm new to robotics, I guess. Well, welcome, I guess. I got an idea recently for a simple robot, and it really would only involve one motor. Like, you press a button, wireless would be ideal, and it turns. I have no idea where to start. I'm actually surprised this one's been upvoted at all. I guess people kind of like the innocence of it. As usually these kind of questions get downloaded. Okay. I'm going to briefly attempt to tackle this one, but obviously there's a lot to go into that. And since we don't have a whole lot of time, I took it all with the first question. Won't be able to get into a bunch. Okay, so you're just talking about one motor. You press a button, and it turns. Okay. You say wireless could be ideal. I'll start with the simple version, and then we'll talk about the actual how to do it wirelessly, because that's more complicated. Okay, so let's start with the electronics first. I mean, the electronics are going to be like, as long as you get the electronics set up, the program that you run on there is going to be fairly simple or something like that. So let's talk about the electronics. I'll give an example using Arduino. So Arduino, just for simplicity. You'll need a battery. You'll need a motor driver. Here I'm using an L298N. You can search that into Amazon, L298N H-bridge, and those will come up. They're really cheap, and they're motor controller boards. You'll also need a motor, and then some sort of, we'll do B for button. We'll have our push button right there. Okay, so these are your components you need. A battery, an Arduino, an L298N, a motor, and a button. So the way that you set this up, now your battery is going to power your motor primarily, because your motor, you're going to probably take like a 12-volt motor. There's other motors, and motors can run off of a range of voltages, but like search for a 12-volt motor. And you're going to have a 12-volt battery as well. So you'll need to find your 12-volt battery. And you can create these using, you can create them using AA batteries. And depending on how you arrange those AA cells, you can actually get 12 volts out of it. That's a little more complicated. If I were you, I'd just search for a 12-volt battery. Or you can find a 12-volt battery pack where it's got all of that wired for you, and you just put in the actual, like AA battery cells or something like that. So 12 volts, you'll need to hook up the voltage, the red wire of the battery to the 12 volts. It'll probably, on the L298N, it's going to say something like 9 to 36 volts or something like that. That's going to be your voltage input. So you'll need to take that, plug it into there, screw it into the in terminal, whatever, and then you're also going to have your ground. So you'll do the same thing there. The L298N is going to have two outputs. It's going to have I think they'll probably be labeled like 1, 2, and 3, and 4, or something like that. There's going to be two of these motor outputs. So an L298N can actually run two motors off of it. Pick one of those. And now here you can actually, the orientation of the wires is going to determine which direction the motor turns. So if you can actually just take a battery and plug it into a 12-volt motor. If you have a 12-volt battery and a 12-volt motor, you can just plug the leads into it. And you'll see if you plug it in this way, it'll rotate a certain way. And if you take it out and then plug it in the other way, it'll rotate the opposite way. So same thing here. And the L298N is just controlling using an Arduino. The L298N just allows you to use an Arduino to control the speed and the direction of the motor. That's all it's doing. And it's just allowing more power or less power to the motor based on some input from the Arduino. Long story short, these leads can run either way. So you don't need to worry about them too much right now. The wires going from the L298N into the Arduino are going to have three wires. You're going to have the enable pin, and then you're going to have, what are they called? It's going to be like drive 1 and drive 2 or something like that. But there'll be 6 pins on here. Okay, there'll be 6 because 3 for each motor. So you need to make sure that the 3 pins that you choose for the L298N are the ones that control this motor port over here. Okay, so it'll probably be, it'll probably be in 1 and in 2 versus out 1 and out 2. It'll probably correspond something like that. So these wires Now the L290N will actually also have a 5 volt output, and then ground. And that's how you'll power the Arduino itself, is you'll power it off of the L290N motor driver. Make sure the 12 volt, Arduinos are pretty good. You can actually plug 12 volts into them and then they'll be okay. But be careful. The 5 volt red wire goes into the VN pin on the Arduino, and the ground wire goes into the ground. Okay, they're just going to share grounds here. Okay, so with that, you've got the wiring set up for the Arduino to control the motor and the battery to supply power for everything. And then with the button, you're going to have 2 leads. You're probably going to do, you could probably do 5 volt on one, and then like either digital read. That'd probably be the best way. Use one of the digital pins. So use like pin 3, for instance. And what you're going to do is voltage is going to go out this way, and I think it's probably, there's probably going to be no voltage and no connection, so this is probably going to read 0 on the digital read for pin 3. And then when you press the button down, that'll probably make the contact. It could be the other way around, but then you'll end up reading 5 volts instead of 0 volts on this pin 3 here. So you can take, whenever that button's pressed, then run the motor a certain way with the Arduino. I won't be able to get into the code. That's a little bit more complicated, but usually this is where people get screwed up. There's a lot of examples out there. I mean, with the code, you're just using 4 pins, because you've got enable 1, and then drive 1 or drive 2, and then you've got this digital read on pin 3. So you can just use pin 3, 4, 5, 6 on your Arduino, and you would be able to do it all. And that's a pretty simple setup. And you can just have it. You can get confused if you don't know, if you haven't worked with it before, on how do you control the L290N from the motor. But there should be enough examples out there to help you out with that. That's a brief overview of how to do that. And also, welcome to robotics. It's I mean, really, this is just kind of electronics, but it's really fun. Glad more people are getting into this stuff. Okay, looking for internship opportunities. I am a junior year of undergrad, and I am looking for internship opportunities in the field of robotics in any research lab. Can someone help me with this? Is there any research lab that is accepting students, international? It's okay if the internship is unpaid. So, now, here's unfortunately the problem. There are not a lot of robotics companies out there. And the ones that do exist are going to be, like the bigger ones that are going to be hiring lots of interns are going to be the companies like KUKA, or any of these industrial manufacturing companies. Now, when you're designing robots for manufacturing customers, these things have to be perfect. And anything less than perfect is totally unacceptable. So you're going to have a really impressive background in order to get a job at one of these places. I mean, you know, like Boston Dynamics, or, you know, an internship. Boston Dynamics, KUKA, Fetch Robotics. I mean, like, people that design the robots there are going to have like PhDs and stuff. So you're going to need to have some sort of resume that's just incredible to get a job at this place. Now, there are a handful of robotic startups, like Slate Robotics, for example. Now, Slate Robotics is not a hugely funded business. I'm bootstrapping everything myself right now. So I don't have a bunch of money to go out and hire interns, as much as I would love to. So your next step, if you can't get an internship at the big boys, NASA, Boston Dynamics, KUKA, etc., then you could look for robotic startups. Now, the problem there is not a lot of robotic startups are extremely well funded. You need funded startups. It says it's okay if the internship is unpaid. I don't hire unpaid interns. God bless them. They're usually more trouble than they're worth. I would rather... And plus, I don't like. I would frankly need to like hire a lawyer to figure out like what's the how like how can I do this legally? Like, is that even feasible? You know, why is it okay that I can hire you for $0 an hour, but it's completely illegal if I hire you for $7 an hour? So like I don't even know the legal ramifications of that, and I would just like it's more trouble than it's worth for me. So I either can afford you or I can't. But anyway, you go out and look at robotic startups. You can look on Crunchbase and you can do a search for robotic startups. Just quick Google search. You can try to find those. There's one. What was it? One. There's one that I follow on Twitter. But anyway, there are well-funded startups out there. But the same thing. The more money that they've got, the more interns they'll hire. But also the more demanding they'll be in terms of your background, and your resume. Which leads me to the third thing, and which is also kind of why this question is a bad question. Because you don't talk about your background. I mean, what kind of background do you have? If you have a big background in robotics and you have a really impressive resume, why are we even having this conversation? Because just go out and get a job somewhere. If you have a great background, people are going to want that. If you don't, and you have the kind of background that's going to make it difficult to get an internship, well, here's a great problem. Here's a great solution to that problem. Just go get your normal summer job. You know, working at, says you're international, I don't know, at Starbucks or whatever. I don't know if they have a Starbucks over there. Just go get a job somewhere, just a normal job to pay the bills, and then spend like 30 hours a week designing your own robot, something you can put on your resume, something that you can add to your portfolio of projects. When I'm hiring people, particularly to do design work, I don't care what kind of background you have. I just care about show me the projects that you've built, show me where you've been effective before in creating awesome robots. You know, because there's this huge disconnect between the theory of all of this. Like you can understand the theory of a PID controller, but you know you don't know you can't conceptualize the difficulty and kind of the intuition needed to to tune a PID controller, right? There's this whole like there's this intuition piece to all of this theory and this practicality and the actual practice of performing, you know, of designing a robot. So you know, I care more about that, and that's my background too. Is like I don't have a college degree in robot design, but you know I taught myself. You know, and even better if you have a great background and you can show me, hey, here's look at all the great things that I've done. You know, that's really the ideal scenario as far as I'm concerned. So probably you're better off just building your own robot. I mean, like pick something like a bipedal robot. Like try to design like a 3-foot tall bipedal robot. That's big enough to where you're gonna probably not be able to just throw on, you know, servo motors. You know, pick a harder problem and do it. That's, as far as I'm concerned, that would go farther. Like I would be much more impressed if someone had a project like that. You know, hey, look, I designed this humanoid robot in my free time, versus, yeah, I was an intern at Boston Dynamics. You know, if you were an intern at Boston Dynamics, I would say, oh, really cool. Tell me also what you've done, like what you've accomplished. So that you might just be better off doing that. I don't know. I'm not Dr. Phil, as much as I want to be. Dude, he has a nice house. You guys got to Google Dr. Phil's house. He lives in Beverly Hills. It's like, I've seen some pictures. That was random. Okay, question number 5. 45 minutes into this thing. I have a mini project to do. So I'm a broke student. It's my 3rd year until uni. You must be British. I study control engineering, and I have to make a mini project about the PID controller. This video is the closest thing I could find to illustrate my idea. I watched the video. It's kind of a cool little project. It's like a little control box where they've got a potentiometer on the output to measure the angle, and it's got a little fan on a motor at the end of a stick. Basically, the fan will turn and it will either move up or down depending on how fast it's turning. So I guess the idea there is that the PID controller, you would try to set the position of the angle based on the speed of the fan. And that's kind of the cool stuff you get to do with PID. Okay, my questions are, how do I start? Is it possible to program it with MATLAB? If so, how can I transfer a MATLAB code into the hardware? Which type of motor do I need? The arm would be a plastic thingy, quite light. And so I don't really know if the DC motor would be too heavy for this thing to fly. I need resources, pulls help. Okay, about MATLAB. I'm going to guess no. You don't need MATLAB. So what you need is an Arduino. You need an Arduino using a PID controller library. Just search for that, PID Arduino. I have PID controllers that I've used with my projects, just using open source PID controllers. I've done some custom tweaking to those libraries based on what I need, but those will work fine for you. Go out and get an Arduino with a custom PID controller, and that's all you need. You'll hook up the potentiometer to it. Potentiometer will tell you the angle, and then you'll just change the goal position of that PID controller based on where you want the motor to be. So, I guess the angle of that bracket. Which type of motor do I need? I mean, just what you want here is high RPM. I mean, you don't need a ton of torque to turn just little fan blades. So I would just go for try to find a $5 DC motor or hook it up to some to an L298N. Don't put the L298N at the end of the arm. Just have the DC motor and run the wires through the arm, and then hook up a some sort of fan blade to it. That's something I don't know too much about, like what kind of fan blades they have. But drones are so popular right now, you should be able to find something. So the question is, no, you don't need MATLAB. And then with the hardware, just use an Arduino and just upload code to that. So search for how to use a PID controller on Arduino, search for how to upload code to Arduino, get familiar with that. And that would just be how I would do it personally. Last question. DIY robot arm software. I'm really into 3D printing, and I've already created a couple of them myself, but now I want to challenge myself by building a robot arm. The mechanics should be pretty straightforward, but I currently know too little about what software and controller board is out there, or whether I'm better off creating my own. With 3D printing, it's pretty easy. You can just use Marlin or any kind of Arduino compatible board. Is there a go-to board/software combination that is a standard for DIY arms? Of course, it would be nice to be able to program the robot by recording waypoints, and it would be even nicer if the software could keep track of the tool head with Cartesian coordinates. If possible, I'd like to be able to add feedback loop to the motors in a closed loop configuration. Okay, so the question's about software that you use for your robot arm. Now this, they say how many degrees of freedom? No. But basically this is a pretty big project. And you mentioned using Arduino. You're probably going to need to use a combination of Arduino and an actual computer. And this is what I do with my robotic arms and with our TR1 and with TR2, is you're going to have your main computer right here, and this is going to be running some sort of operating system, so you can do your programming on. Then you're going to have so this is kind of a dumb example, but you're going to have all of these. It's going to depend on how your hardware is set up. But basically, you're going to need the CPU to some way be able, this operating system to some way be able to read the angles of the different joints and also send commands. So what I do with TR2, for instance, is that I have an actuator for each joint, And each actuator has an onboard NVIDIA, or I'm sorry, an onboard Arduino. And that Arduino has, right now, Bluetooth, but I'm probably going to move to ESP32s and start doing it all by Wi-Fi. I've done I2C in the past. I2C is an okay solution. You'll be able to get it to work. I2C has a whole bunch of issues that I won't get into. UART serial is also a good solution. So you need some way for the CPU to send out commands and read. The way I do this, again, all of these joints have their own Arduino with their own onboard communication, and they're able to read positions, set positions, and I have a whole protocol built out for how do you send a command from here to here with checksum, error checking, and all of that. Like it gets a little complicated. I spent several months trying to build all this out. I'll start with the way we do it complicated, and then I'll try to break it down to maybe an easier way. But this is the way that so this is an Arduino Mega that we use this in TR2. And the USB output for the main computer running an operating system, we'll say Raspberry Pi or an NVIDIA Jetson, that's hooked up to the serial port on the Arduino. So those included USB cables, you can plug that into the USB of the CPU and then plug the other end into the Arduino. And that will, if you've got the drivers installed on here for the operating system, you'll be able to read and write serial data from this Arduino to the main CPU. Okay, you with me so far? From here, it's much easier to communicate. Once you have connection with one Arduino, it's much easier to communicate from Arduino to Arduino. So what you can do from here, now that you've got this set up, this is your router, essentially. And this is communicating with all of the actuators. So the CPU is going to be sending some series of commands from the CPU to the Arduino. I have a whole bus architecture where we have a bus address for each of these actuators. And then, so the CPU will say address 5, move forward, rotate forward at 100% or something like that, for also this duration of time. So I'll send that here, and then the Arduino will figure out how to get that data to that main actuator. So right now I have Bluetooth modules hooked into this Arduino, which are the master Bluetooth modules, and then these are the Bluetooth slaves, and then it'll use Bluetooth. And depending on, and Bluetooth's 1-to-1, which is kind of the problem, but you'll be able to send the data out that way. What I've done in the past, and the reason this is so complicated, what I did in the past is just hook up I2C, like NVIDIA Jetson, almost all single board computers like Raspberry Pi, they're going to have available I2C interfaces for the boards. And what I've done before, which is, it's a fine protocol, it wasn't designed to be used for long distance communication like this. I2C was designed to be used just on a printed circuit board, but it works. This is the kind of stuff where people will tell you, you can't do that, and like people on the robotics subreddit will just crap on you because of things like this, right? Like I2C wasn't designed for this, but my point is always like, well, if it works, it works, But anyway, you can use I2C, and that makes it relatively easy. And you just hook in these 2 wires to every one of these, and you just tether them together like that. That would be a simpler solution. So I would look into I2C. The problem that I had is that, particularly with NVIDIA Jetson, these boards are so sensitive to changing voltages on I2C. I have destroyed thousands of dollars worth of boards from these NVIDIA Jetsons because the I2C is so sensitive, and if this Arduino for any reason sends back a voltage it doesn't like or draws too much power or something, the I2C bus on this board just completely goes down, and it's down forever. And like the HDMI is hooked up with the I2C somehow, and it's just this whole thing. So by using the USB serial interface, it's more reliable and we have less problems and it doesn't destroy the boards. So that's why I went there. This is the whole network topology problem, which is, it's a really complicated problem. Trust me, I've spent many long sleepless nights trying to figure out the best way for this. And I've got what you're wanting is high bandwidth with all of this. And you want reliability and high bandwidth, because you want these angles in these actuators. You want them to just blast that their angles and their joint positions back to the main computer just at a very high rate. And you'll find with I2C and with other protocols, you can be pretty limited on terms of how much data you can be sending back. So Bluetooth works the best so far. It has the problem of being incredibly complicated and requiring a bunch of different modules. And then my next step is, ESP32s with Wi-Fi seems pretty, well, it looks great. It looks like it could work. Okay, so we've got a main board computer on an operating system that's able to communicate with either you're going to have a central control box here where it's going to do all of the logic for the whole arm, or you're going to have encoders and or you're going to have actuators that have their own intelligence on each joint. Either way, your main computer is able to command and read the robot arm. So the reason we've done that is because now you can run like a simple Python script that is going to change the position of each of these actuators. So what you can do is have, like, you can have an Xbox controller where the Python program is going to read the Xbox controller, and then if you move the joystick, it's going to move this joint. And then you have another button that reads, it sends out a command and say, hey, send me back joint position. And then you can set the position there, move the arm, and then set the next position. And you can record those waypoints that way and send a command back once you've recorded all of the angles for each of these and say, you move to this angle, you move to this angle, you move to this angle. You can wait for it to actually get to that position and then move on to the next waypoint. So it's a complicated problem. I mean, it's a pretty complicated problem. But that's the simplest program you can have running on here to just do waypoints. You can look at integrating your system with ROS. That's a whole shebang you could probably spend a month on if you don't have that much time to work on it and if you're not that familiar with ROS. And that would allow you to use different packages that can actually do the recording of the waypoints and the commanding of the waypoints yourself, or through the program itself. There's a lot of overhead to getting that set up, but it might make your life easier ongoing, going forward. I do know there are CNC and G-code readers for like robotic arms. I don't know if you'll need to get set up with ROS, but you're going to have you're going to have to define your robot in some sort of way that's going to be able to feed into those systems. I would guess that ROS probably has some sort of open source G-code reader as well, or parser that could actually command your robot. So if you're wanting to go big league with this, I would integrate with ROS and try to find some open source G-code parsing packages. And if that doesn't exist, message me, because we should build that out. Like, that would be great. Because I have a lot of things that I would like to do with that. I mean, there's a bunch of stuff you could do if you could send your robot G-code. But I'm sure somebody's come against that. Okay, wow. Hey, we're about at an hour. I said 30 minutes. So if we're just under an hour, that's not too bad. I hope this was valuable. This is a lot of fun for me going through these questions. All of these questions were posted in the past week. So this might be just a good way for me to do this podcast going forward. Video podcast. It's not really great for listening probably. But yeah, this is great. So who knows? Maybe next week I'll do more questions. But if you guys have any questions or anything else that you would like me to clarify, maybe for the next podcast, or if it's a simple question I can answer in the comments, ask it below. Be sure to subscribe to Slate Robotics. Don't click the notification bell. I don't use that ever, so don't do that. And yeah, follow along. Visit our website, slaterobots.com, for more information about our TR2 and our upcoming product launches. That'll all be posted through our social media sites and all that kind of stuff. So thanks for tuning in today. I've really enjoyed it, and you guys have a great week.